So we're going to shift away from pure compounds. This past few lectures we've done PV diagrams and PT diagrams for solid, liquid, and gas, but for a single compound. So we had like water. It was a whole diagram for water, and then a whole diagram for CO2 and those kind of things. Last time we had the three-dimensional version of it all. But today we're going to get into mixtures. So binary mixtures, where we have the x-axis is also labeled X typically. It's composition. So these are going to be PX and TX phase diagrams. So pressure, composition, phase diagrams. And so this is where we start getting into ideal and real mixtures. And so let's talk a little bit about the Gibbs energy of mixing. Remember, Gibbs energy determines what's spontaneous. And so we know from our experience in chemistry that sometimes things mix and sometimes they don't, right? We say oil and water don't mix. If anybody says that to you now, you could ask, but wait, what temperature, right? Because it could be a high enough temperature where they do mix. And so we'll see here in these equations where temperature figures in. So here's the delta H of mixing. And we talk about ideal mixtures. See, it's a conditional. So up at the top, it's equal to 0 if we have an ideal mixture. And if it's not equal to 0, there's lots of theories for calculating the delta H of mixing. So this is one theory that I'd use in my research, the Hansen theory on mixing. And this is Hansen's determination of the delta H of mixing. And it uses these terms here. There's Hansen and Hildebrand. Hildebrand started this, and then Hansen refined it. But these are things known as solubility parameters. And that's the thing that scientists have been doing, is been trying to figure out how do we correct for non-ideal behavior. And so this is these are, well, right here, the solubility parameters. Just put an arrow down to that. We're not going to do anything with those today, but we're going to have a whole lab dedicated to them. And it's essentially a way to capture the energetic penalty or benefit from mixing two things. So, and then what about the delta H? So that if there's no intermolecular attractions, there's no differences on mixing. But if there are intermolecular attractions or repulsions, then we'll get into how to model that with the Hansen theory. And then we have the delta S of mixing. So this is the slope with respect to temperature of the Gibbs energy of mixing. And so then we have this based upon multiple mole fractions. These X's are mole fractions. And notice mole fractions are always less than 1. So mole fractions so that means all of those natural logs are negative. So they cancel the negative sign. So this means that the entropy always increases upon mixing. Now this is not just for molecules, this is for marbles in a jar or M&Ms in a bag. Like if you were picky and you put all the M&Ms, like you had a particular order of the color, and you put the green ones on bottom, and then the yellow ones, and then the red ones, and then you drop the bag, what's going to happen? They're going to mix, right? Because again, they have the whole volume of the bag. They're going to expand to take the whole volume, because that lowers their energy levels, and there's more energy levels populated. And even though M&Ms aren't quantized, this is just built into nature that spontaneous mixing mixing is spontaneous, driven by entropy. Okay. And so then this is the delta G. So as long as delta H is 0, or in some cases negative, exothermic, then we have a spontaneous mixture. The only barrier to mixing would be enthalpy. So if enthalpy is positive, then you might prevent mixing. And so with the ideal solutions, we just have this nRT and the sum of all of these mole fractions and their logarithms. Okay. And remember that these xi's are negative, so therefore these natural logs are less than 1, and these natural logs are negative, so their Gibbs energy of mixing is going to be spontaneous. Okay. for ideal solutions. Let's talk a little bit more too about the Gibbs energy. There's another name for that. And think about our physics class, our mechanics physics class. You got a ball on a hill, right? That's potential energy. And so we want to know, if we want to look at the energetic, classification of things, the landscape, we could calculate the potential energy for everything. We do the same thing for chemistry, and we call it chemical potential. So the Gibbs energy is the chemical potential of all chemicals. Just like potential energy, a ball on a hill, it has a lot of potential energy. It could roll down with lots of momentum and so on and do things. Same with chemical potential. If we have Gibbs energy, we can analyze that and see what kind of reactions are possible. So now when we're at equilibrium, the delta G going from any spot to any other spot in that container or that system is going to, if we're at equilibrium, is going to be zero. So that means the chemical potentials of all of the objects, the chemicals in that equilibrium system are the same. So this is an important principle here, that this chemical potential we're calling mu. So the molar Gibbs energy is often given the symbol mu. And so it's just saying that the chemical potential of this A liquid state and is the same as this A, and should be B. I've got a little typo there. Put a B on one of those. Okay. And the thing that's going to drive those to equilibrium, we're going to have different concentrations in the gas, different concentrations in the liquid, and it's going to drive itself forward spontaneously until all of those chemical potentials are equal. Okay, so these are some essential terms. Those are some background terms, but these are essential terms. So that's why I put a huge slide here. Enormous font. So in all the next several days and weeks, we're going to be talking about a lot of mole fractions. So these are all mole fractions. But when we use X, we're dealing with the liquid phase composition. When we're dealing with Y, it's the gas phase composition. And Z is going to be the overall composition in the container. So like in this room, I've got water in this can, and I've got water in the gas phase in this room. And I could take the number of moles of water in the whole room and divide by the total number of moles of everything in the room, and that would be Z. Okay. If I took the moles of water vapor divided by the moles of vapor, that would be Y. And if I took the mole fraction of water liquid and divided by the total moles in the liquid state, that would be X. So just keeping that straight is important. The next foundational principle, we've kind of already talked about Dalton's law, where the partial pressure of each of the gases adds up to the total pressure. And so this is what we see here. Like if we have the partial pressure of B and the partial pressure of A, that will add up to the total. So all of these lines going up, the two crisscross lines are Raoult's law. So these are Raoult's law lines here and here. But then Dalton's law is this line up here. So the pure vapor pressures are indicated by these little stars. So substance A has a particular vapor pressure, substance B has a particular vapor pressure, and this whole chart is at a given temperature. So the whole chart. Y'all read cursive? Sometimes it's faster for me to write in cursive. I have to ask nowadays. Yeah. My kid's teacher had a really cool thing. She called them the cursive conquerors, and it was an extra credit type thing. And if everybody worked on their penmanship in terms of cursive, then she took them all out to dinner at the end of the year. So it was kind of nice. So the whole chart is plotted at a given temperature. So if we change the temperature, then all of these curves will shift. The pure vapor pressures will drop if we cool it down. They'll go up if we heat it up. And all the crisscross lines will move, and the Dalton's line will move. So this is a particular slice at a given temperature. Now we can look here and we can see that at this temperature, this is the boiling temperature for this mixture right here. So about what would you say, about 0.3 moles of A in total moles. So that would be the boiling, this chart, that Dalton's line crosses 1 atmosphere at 0.3. It's just coincidence. Yeah, it's just coincidence. Now, if we were to now, let's ask this question, a little trivia question: A or B? Which one? Which one? A or B? Those are your two answers: A or B. Which one of those? And think of your answer in your head, and then I'll ask you to say it out loud all together. So we'll see how many people say A, how many B, without calling you out with raising hands. Okay? So get your answer in your head. Which of these substances, A or B, is the most volatile? Which of these substances, A or B, is the most volatile? Now, say your answer out loud on three. 1, 2, 3. Yes, A has the higher vapor pressure, right? So it's got the highest vapor pressure, and so then it's going to have the lower boiling point. And that makes sense, right? If we were to cool this down, all of these lines would drop, and eventually you'd have PA right here at the boiling point of A, and all of these others would go down too. Does that make sense? So at a cooler temperature, this is what it would look like. Because A is the more volatile substance, and so we cool everything down and until like A is right at 1 atmosphere. If we warmed it up until B was right here, then we'd be at the boiling point of B, and A would be way up here. And so every one of those mixtures has a different boiling point. So we can adjust that temperature until whichever mixture is at 1 atmosphere, and then that mixture is the boiling at that atmosphere. Okay. And this is the beginnings. We're not there yet, but this is the pressure version of distillation. We're going to later switch to TX plot, where we have temperature on the y-axis, and we can follow boiling points all day long. Okay, so all right, so let's look. That's kind of what I was showing right here. So this is the pressure at 298, and then yellow is the pressure at 280, and orange is the pressure at 270. So we're cooling it down. And so the boiling point of A is right here, because that's our 1 atmosphere line. Okay, so this boils at 270. This mixture here boils at 280, and of course this mixture here boils at 298. Okay. And that makes sense, because if we're coming off of pure A and we're adding in B, B is less volatile. So it makes sense that if we're adding in something that's less volatile, we're going to have to raise the temperature to boil that mixture, right? Because it's less volatile. There's less vapor pressure coming off of that. So we'd have to raise the temperature to get the whole mixture to have a 1 atmosphere vapor pressure if we start mixing in something that's less volatile. Okay. Y'all interrupt me if there's anything that you want to ask about. Okay, now it gets a little complicated. So the lines we've been showing here are the lines, the P lines based upon the X composition. But what's the composition in the vapor phase? So after the vapor leaves the surface of the liquid, you're going to have, you don't always, but you can have different concentrations in the vapor phase that add up to the total vapor pressure. And so that's this YA. So this is the vapor phase composition line. So compositions of the liquid phase and the vapor phase are not the same. Bang, bang, bang. Beating that into you. It does make sense. If something's more volatile than the other, it's going to be concentrated in the vapor phase. Does that make sense? The more volatile compound is going to have more molecules in the vapor phase than the less volatile compound. And so this map of pressures and compositions at which each phase is stable is shown here. And this is our calculation of the vapor phase composition. So let's say we take a 50-50 mixture. So we're going to sit right here at 50-50. And we come all the way to the top. So there's our 50-50 composition in the liquid state. So this black line is giving us the liquid state, and it's going to have a vapor pressure right here at whatever temperature we're working at. So this is PVAP. For the 50-50 mixture. No problem with that. Anybody have any problem with that? We come straight up to the black line, and that's the vapor pressure of that mixture. Okay, but what's the composition of the vapor? We keep that straight line over here till we hit the red line. And that red line tells us that we have like a 60, let's see which one, yeah, 60% A, 40% B. So the liquid state has 50-50, but the vapor state has 60-40. That's weird, isn't it? But it makes sense if you think, yeah, A is more volatile, so we should have 60% A or more A in the vapor phase than we have in the liquid phase. So if you pull it, it's at equilibrium. So this is at equilibrium. So A is still going in, but I mean, it would be, think also about how much less molecules are in the vapor state than in the liquid. So the liquid contains 99.9% of all of the molecules of both A and B. And so it hasn't really moved the needle much on the liquid. But the small number of molecules that are in the vapor phase are concentrated in A, 60-40. So we really can't detect that much of the A is missing from the liquid. But if we were to capture that A, or capture the whole condensate, then we would eventually deplete the liquid from A. And what would happen to our liquid composition? It would move left. Like if we're pulling A out of the container, then the liquid would start to move left. And if we keep doing that, we're distilling it. We're pulling A out, the most volatile compound gets pulled out of the mixture, and the liquid is the still bottom, and it becomes more concentrated in B, because we're preferentially removing A. So yes, over time, you can deplete the liquid, but if it's just a 50-50 mixture, and you look at the vapor, if you were to condense that in one shot, you would say, wow, it's 60% A. But you go back to the liquid, it's still 50-50 because very little molecules on a mole basis have left the liquid. Now, when you have, look at this Y vapor. So it's kind of like a a string tied at both ends. See how it's kind of loose, this string? It gets further and further away from the black line, the more different these vapor pressures are. So look here, this is the difference in vapor pressures. What happens if this is if they're equal? If they're both the same volatility, then this goes to 0. And so that kills this piece. And then we just have, XA, PA over PB. If they're the same, remember this difference is 0, then they're the same, and YA equals XA. So if there's no difference in the volatility, then there's no difference in the vapor phase composition. They're both just as volatile. So a 50-50 mixture in the liquid would give you a 50-50 mixture in the gas, and it would be impossible to distill those from each other. They'd essentially have the same boiling point. They'd have the same vapor pressure. So when YA equals XA, when PA star equals PB star. Really good question, but we're not going to get into those. Is this difficult enough to do binary mixtures? Yeah. And so, but from that Gibbs energy, the first equation I showed, the Gibbs energy of mixing and then the entropy of mixing, notice the entropy of mixing was universal. It had a sum of all of the components. And so we can easily say that spontaneous mixing is, the entropy of mixing is spontaneous for all mixtures, no matter how many components. And it just becomes more and more spontaneous the more components you have. So yeah, it's just, you add more and more positive terms to that entropy. Okay, so then let's look here. Basically what I just drew is this right here. So in this case, our boiling, if we boil this liquid at XA, it's at 1 atmosphere now. And then if we condense this vapor, so it goes off the boiling flask into a condenser and drips into a collection flask, then the collection that we would have would be right here. It would be the YA value. We've recondensed it and now it's a liquid. Okay. So this is the basis for distillation. And of course, you remember from organic, the further apart the boiling points, the easier it was to separate the liquids. That's here we're saying the further apart the vapor pressures, the easier it is to separate the liquids. Okay. Now these are ideal graphs, ideal situations. Let's look at some non-ideal situations. So this is a crazy one, acetone and carbon disulfide. So the dashed lines are Raoult's law, and then this is the experimental values, these blue lines. So that's kind of crazy. You know, this is carbon disulfide is the most volatile of the two. And in previous charts, the most volatile was the maximum, right? So this was the maximum pressure in the whole chart. Well, when we have non-ideal solutions, the maximum can be somewhere else. Like here's the maximum in this chart. So that's a little strange. It's more volatile than carbon disulfide is by itself. So there are substantial deviations from the ideal partial pressures, which is what we get down here. So these deviations right here. And then when you add those together, you get the Dalton's law line. So this total one is still Dalton's law. That's never broken. You just add up all of the partial pressures in the container, and that's your total pressure. So they have a lot of time to interact, and so we've come up with another law to kind of govern these situations called Henry's law. Now, why would it be that this total pressure would be so much higher? Well, if you think about this, acetone does have some ability to, well, it's got a dipole. So it's got a molecular attraction that makes it less volatile. You see its pressure, the acetone vapor pressure is over here, pretty small, 230 torr roughly. And so why is that? Well, it's because the acetone likes the acetone, like they bond together. So and carbon disulfide doesn't really like itself. I mean, it's very volatile. If we mix in some acetone, what happens? Well, the carbon disulfide is actually getting in there and interfering with the dipoles in the acetone. So it's interfering with the thing that's holding the acetone in solution. And so then the total vapor pressure is much higher than the carbon disulfide by itself. Yeah, it's not the area, it's just these marks right here. So like if we pick that one and we pick that one, then that's the sum of those. So it's just vertical. Yeah. So I'll call this U and V and T or something. So T is equal to U plus V. Does that make sense? So it's just at each composition point, you get the total pressure by adding up the vapor pressures of the components. And that would work for 3 and 4 and 5 component mixtures. Yeah, I see what you're saying, but if an integral, if we were to like integrate from left to right, the integral would look like a big S curve, right? It would look like, say, yeah, if we were to integrate this, we would continue adding, and it would go up, and it would go up here like that, and as we add from the left to the right, that sum would continue to increase. It's kind of like when you integrate a peak, you've got a peak like this, and you integrate that, it looks like this. Yeah, and so this curve comes up, but then it comes back down as the vapor pressures get over to this side. The influence of acetone drops off suddenly, and then you're back to just the carbon disulfide. So here are the two laws governing both ends of this composition curve, Raoult's law and Henry's law. So the ideal solution, this is obviously that straight line from zero to, so this straight line from zero, like if we have 0B, then our vapor pressure B has to be zero. So it has to be pinned at zero on one end, right? And there's no B, so how can you have a vapor pressure of B? And then at pure B, we want to hit the vapor pressure of B at that temperature. So this dashed line is the ideal solution. But when we have a non-ideal situation, it deviates from the ideal dramatically. So let's look just at this region here. No matter how curved this crazy curve is, it'll start out linear, right? And even like the derivative of sine is cosine. What's the very first value of cosine? 1, right? So the slope of sine is 1 as it crosses 0. And it's a linear line. I mean, it's just the slope of 1, y equals x. And so no matter how curved the curve is, if you narrow your window down, you can model it with a linear equation. Okay? And so that's what Henry's law is. It's just applying a linear equation to this really dilute region here, and then extrapolating it all the way across to the Henry's law constant. So that's the Henry's law constant. And you see, it's really kind of a stand-in for PB. So focus on the limits. In dilute solutions, they're dominated by individual particles of B that may or may not have an attraction to the rest of the liquid. If they don't have an attraction to the rest of the liquid, they can have a really high vapor pressure. Let's say they're in a polar solvent and they're polar, then they can be really attracted to the polar solvent and have a really low vapor pressure. And then concentrated solutions of B are dominated by the properties of liquid B. So here are the equations that go with this. So if you're dealing with concentrated solutions, so notice B, when it's concentrated, matches Raoult's law in this tiny little region. And so this is just the vapor pressure of B is equal to the mole fraction times the pure vapor pressure. Can I say VP for vapor pressure? Pure VP at T, and the whole chart is at a given T. And so let's say we have only 95% B. Well, that's pretty concentrated B. It's 95% B, but it's not pure. So it's not going to have its pure vapor pressure. It will have 95% of its pure vapor pressure. So this is pretty easy. You just take the pure vapor pressure, multiply by 0.95, and you have the new vapor pressure of B. So Raoult's law is just XB times the pure vapor pressure of B. Super simple equation. And it goes to zero as mole fraction goes to zero. But Henry's law, if B is the solute, so now you have B down here. Clearly, if we have zero B, we have zero vapor pressure. But what if we have 5% B? Then we have 5% of the Henry's law constant. If we were to say 5% of Raoult's of the vapor pressure, we'd be right here. And you see that's not accurate. We would want to say 5% of KB would give us an accurate value. So this would be sort of P Raoult's law, RL, and this would be the P Henry's law, HL. You see how far off we are. We're like 100% off. So Henry's law will give us a more accurate pressure of dilute solutions. Okay. And this mess in the middle, we're going to talk about that in a little bit. Okay. So here, we have to come up with some other kind of theory to deal with the middle range. But we can do both ends pretty easily. If it's concentrated, like if the mole fraction is like 90% or more, then we would use Raoult's law. If it's less than 10%, we'd use Henry's law. And of course, if it's an ideal solution, KB and P star equal each other. So you can compare KB, the Henry's law constant, to the vapor pressure, and if they're very different, then you know you have a non-ideal solution. Okay, let's look at these two different mixtures, like a tale of two cities, but a tale of two mixtures. And we've got the compounds on the left hate each other. Why do I say that? Yeah, they're off scale. Yeah, but also just look at the total pressure. If I mix these substances, most of the mixtures have a higher vapor pressure than either of the components. Okay. It's like this is the vapor pressure of carbon disulfide right here, pure carbon disulfide. And if I put any acetone in there at all, it prefers to be in a vapor state. It's like, I hate being with the acetone and acetone hates being with me. We'd prefer to be in the vapor state where we don't have to interact. If the liquid, they have to touch. And the gas, they don't. Okay. And what about the solution on the right? They love each other. Chloroform and acetone would prefer to be mixed rather than separate. And that makes a little bit of sense. We could think of this in terms of the positive interaction. So we have acetone with this double bond, oxygen here, and then we have chloroform. And so we can form this hydrogen bond between them. Chloroform can't really hydrogen bond with itself, and acetone can't really hydrogen bond with itself, But you get them together, and now we have hydrogen bonding that can occur. And hydrogen bonding is pretty energetic. And so that's why this mixture that's close to 50-50, it's not exactly, because the compounds don't have exactly the same vapor pressure, but almost close to 50-50 is the lowest vapor pressure, because that's the pairwise sweet spot where we have as many acetones as chloroforms, and they can hydrogen bond with each other. And also, if you look at this, the Henry's law constant for acetone in chloroform is much lower than the vapor pressure of acetone. So you can compare that. Henry's law constant, if it's less than the vapor pressure, this is a situation where the molecules like each other. If it's way worse or higher than the vapor pressure, that's a situation where they dislike each other. And so this is just the molecular view. Notice how we're talking about non-ideal behavior, because if you think about this, this solute, whoa, what happened? Let's see. Okay, we got it. No. Let's see if this fixes it. Oh, something just blinked on my screen, and now I have no access to my pen. You see my mouse? No. Bad word. Okay, so we have, think about this. This little molecule here has no access to its nearest neighbors. And so it makes sense that its behavior will be different. Now, maybe it's attracted to the blue molecules, in which case its vapor pressure would be lower than if it was in a pure, gray ball state. Or maybe it hates those blue spheres and it would rather be in the vapor phase. So, thinking about what's happening in the liquid state is what is going to give you insight into the vapor phase. So we can do experimental data and collect pressures, partial pressures, and total vapor pressures, and that's what these experimental dots are. And we can come up with activities and activity coefficients. Man, I really need my pen. All right, fix this. Can't see what I'm doing, but oh, okay, it's back. Wonderful. I don't know what I did. Just punched a bunch of buttons. Okay, so what we do is we want to correct this vapor pressure and come up with an experimental vapor pressure in the middle region. So this is not Henry's law or Raoult's law. Activities, let's say for the middle. So in this region, from right here to probably right here. Concentrations. Thank you for asking. I got some extra gaps in there because what it's done is my tablet is normally half as big because I'm extending my screen. Now my tablet is covering the whole, so the cadence of my writing is soft. So notice that these ends right here, even experimentally, this is Raoult's law for the concentrated species, right? This is Henry's law right here. Okay, this for the CS2, this region right here would be Henry's law. This region right here for the acetone would be Raoult's law. And so this region in the middle, we have to calculate, or we have to collect data. We can't use just the pure vapor pressure and so on. So we would take Raoult's law, this is Raoult's law right here, and correct it with an activity coefficient. No, that's a gamma, not a Y. Yeah. So this is gamma. So I'll write that up here, gamma. And notice it's just converting. I mean, it's just going to be some number that's less than or greater than 1. It can make the vapor pressure higher or lower. And that's going to give us the activity. So instead of the real vapor pressure, it's going to be giving us the activity, or the theoretical or Raoult's law vapor pressure will give us the activity. Okay, and so we can measure those, and then if we try to figure out a curve that goes through them, then we could have a model. And so there are some models that we can use. The one that I put in the notes, oh man, I can't believe we're out of time, is the Margulies equation. So the Margulies equation can help us model that region in between. So this equation will give us, with this beta parameter, notice that over here, we've got some realistic looking curves, right? These look like what we've seen with the experimental data, don't they? They've got that funny shape. They have Raoult's law and Henry's law on both ends, and then they have the funny shape in the middle. And so I've got a spreadsheet version of this that I'll put up on Blackboard where you guys can play with it. And so here we've got the Raoult's law curves, we've got the dashed lines of the Henry's law curves, and we've got these funny shapes that are given by the Margulies beta. So you can type in the beta and you can get all of those different shapes. Now, the nice thing about this is if you measure the vapor pressure of a 50-50 mixture using a pressure gauge, then you get a data point, and you can get solver to adjust your beta to drive that total line through your data point, and then you'll have all of the activities for all of the gases. Okay, it's probably not accurate enough for chemical engineering, but it is pretty good. Okay, and so I'll give you that, and that's something that was the result of some projects that our students did in the master's program last time I taught thermodynamics. So we made this a class project for them, and so it turned out pretty good. So we're out of time. Let's see how many. Yeah, perfect. That was the main point I wanted to get to, was this spreadsheet, and then I'm going to put that up on Blackboard. So y'all can play with that since you have no plans over spring break. You didn't exactly say no plans, but.